My name is Joseph Azevedo and this is my lab report for Lab 4. In this report I'm going to go over the purpose of the lab, the fundamental physics principles involved, the procedure involved and the analysis performed at each stage, where I ended up estimating the time constant of a simple resistor-capacitor circuit to be 5.998 seconds, which is within 0.002% of the expected value. Finally, some follow-up questions about the lab contents. So, starting off, the purpose of this lab was to explore the properties of circuits involving capacitors and resistors, and to apply our knowledge of fundamental circuit principles to make predictions, gather measurements, and perform analysis for various aspects of the circuits as they operate. Throughout the lab, we're going to rely on a handful of fundamental physics principles, namely, the flow of current throughout circuits, the node and loop rules for circuits, Ohm's law, the relationship of capacitance, voltage, and charge for an ideal capacitor, and the behavior of capacitor-resistor circuits over time, and with that, the idea of a time constant. We started off in our first circuit system by using a simple series circuit consisting of two batteries and two resistors, with the shown voltages and resistances. I first predicted the current at two different points in the circuit, I1 and I2, to be 20 milliamps, and this was verified when using the simulator. Also of note, these values don't change even when reversing the ammeter. I then replaced one of the ammeters with a voltmeter and measured the voltage across the two ends of the now open circuit, where no current is flowing, which measured -3 volts. This is because the red and black probes of the voltmeter are connected in the loop in the same orientation as the batteries, and since the round-trip time in the voltage must be 0 according to the loop rule, the observed voltage drop across the two wires must be the opposite of the potential across. After reconnecting the wire to make the circuit closed, I measured the voltage drop across various components in the circuit, and the chart shows the potential in the circuit depending on its position. In a slightly different configuration, where we attach an ammeter in parallel with the 100 ohm resistor, we observe that the current reading is 60 milliamps instead of the 20 milliamps that it was before. This is because the ammeter essentially acts as a wire, and since current tends to follow the path of least resistance, the current entirely bypasses the 100 ohm resistor. As a result, the 47 ohm resistor is the only relevant resistance in the circuit, and applying Ohm's law yields a current value that coincides with the ammeter's reading. The next part of the lab focused on a different circuit system, namely an RC or resistor capacitor circuit containing a 9-volt battery, 10 ohm light bulb, which acts as a resistor, and a 200 millifarad capacitor. The circuit ran through multiple stages over time. First, the initial state saw no charge in the capacitor while the bulb started out being unlit. Immediately after connecting the circuit, the light bulb lit up, and over time it slowly dimmed as the capacitor gained charge. Then, when I replaced the battery with a wire, the light bulb immediately lit up again and slowly dimmed as the capacitor discharged. With these behaviors noted, I measured the time it took for the capacitor to both charge and discharge in two different configurations with 10 ohms and 20 ohms, as displayed in the table. The final part of the lab involved another simple RC circuit, this time with a 9-volt battery, a 30 ohm light bulb, and a 200 millifarad capacitor. By using the simulator to track the voltage running through the circuit over time, I was able to record multiple voltage values while the capacitor discharged, and use them to plot a graph that would let me determine the circuit's RC time constant. This comes from a modified version of the formula of the time constant, which is expressed as a linear equation with the time constant being the negative reciprocal of the slope. By plotting the natural logarithm of the potential ratio between the current and initial voltages, I was then able to use least squares linear regression to find the value of the RC time constant, 5.998 seconds. This corresponds to a negative 0.002% error compared to the predicted value for the RC time constant, which comes from the resistance multiplied by the capacitance, and serves as a testament to the simulation's accuracy. Now that I've covered the procedure and results of the lab, I wanted to touch on a few follow-up questions. First, if we were doing this in real life, we know that physical ammeters, and most conductors for that matter, have resistances of their own, which means that connecting the ammeter directly changes the total resistance of the circuit, and, by extension, will change the current of the system. Ultimately, this likely would have resulted in a slightly lower value for the measured current. Additionally, if we used a real battery to charge a capacitor with no resistance, our model predicts that the capacitor would instantly charge, but since all the components in the circuit do have some resistance, it's impossible to obtain the zero net resistance that would cause an instantaneous change. Moreover, we also know that batteries don't have a perfectly constant EMF value over time, as they wear out and discharge. In conclusion, in this lab, we explore the properties of circuits involving capacitors and resistors, and we used our knowledge of fundamental circuit principles to make predictions, gather measurements, and perform analysis for various aspects of the circuits as they operated.